Hello and welcome to this section of the Calculus Derivative Help Tutor. In this section we're going to talk about what we call the natural exponential functions. Right? So you've all probably been exposed to exponential functions before. Here we're going to talk about a very specific natural exponential function that basically means that the base is going to be e, this very special number e, raised to the power of x. So all of the functions we're going to deal with here are going to be e raised to the power of x. And you may not have studied that function too much up until now, but I promise you e to the power of x or any function that resembles that is a very important function in all of science and engineering, and it'll pop up over and over and over because e is such a special number. So what we're going to do is talk about, in general, e to the power of x. Now remember, this is just a number, 2.7 something, raised to the power of x. And I want to go ahead and give a little bit of background to it, just so you know where we're coming from. So I want to tell you that e raised to the power of x is what we're going to call inverse, which you've probably studied before in algebra, is the inverse function of the natural log of x. Now that shouldn't be too much of a surprise to you that this function is an inverse of this function, because the natural log is a logarithm with a base e. So there's a base e wrapped up in here, so there's an e wrapped up in here as its base over here. These guys are inverses of one another. Now you probably studied inverses all over in algebra, but in this context, when we say inverse, what I'm basically saying is the following thing. If I take a natural log, and instead of putting x inside of here, if I put in e to the x, which is its inverse, what do you think I'm going to get back? I'm going to get back x. So literally do this in your calculator. And so forget about x for a second. If I take the number 2, make x equal to 2, and take e raised to the power of 2, e squared, and I get a number. And then I take the result of that, and I take the natural log of the answer. Then what I'm going to get back is 2, right? It works for whatever number you put in there. You put 1500 in for x, e to the 1500 power. You're going to get a big number. You take the natural log of the answer that you get, and you're going to get back the large number, the 1500 that you started with, right? And that works for everything because they're inverses of one another. And consequently, because this is true, the following is also true. If I take e, the other function, and raise it to, instead of x, raise it to the power of the natural log of x, I'm going to get back x as well. And this is sort of the definition of what an inverse function is. Two functions are inverses if basically you plug one function in to the other one and you get back, your variable back, basically in this case. So that's what's going on here. Now this is sort of an aside, just to kind of get you familiar with these guys. It's not really calculus here, but it is very important because you can actually use these properties to solve equations. Just as an aside, what if you had an equation like, e to the x is equal to x plus 2. Or actually, let's take this away. E to the x is equal to, 3. How would you solve that equation? If somebody said, hey, solve for x. Well, you see, all growing up with algebra, right? Or geometry and trig and these other math classes that you've had, especially algebra, you've learned how to solve equations. You were taught that the opposite of addition is subtraction. You were taught the opposite of multiplication is division, and you were taught to isolate variables by just dividing or multiplying or adding or subtracting to isolate the variable you want, right? You were taught that the opposite of a square root is to take the square of something. So you can basically remove a square root by taking the square of both sides of an equation, right? So here, how would you isolate x? Well, you can't add or subtract or multiply or divide. The only way to do it is to take the inverse, apply the inverse to both sides. So in other words, if I basically take the natural log of both sides of this equation, I have to do it to both sides because it is an equation. I have to do everything to both sides. Then on the left-hand side, because of what I'm telling you here, the natural log of its inverse gives you the variable back, then all of this stuff disappears. And on the left, all I have is x. On the right, I have natural log of 3. And you can stick this in your calculator and get a decimal answer back, and you've solved for x. So that's how you solve equations that deal with exponentials. You can also do it with equations that involve logarithms. If I have a logarithm on one side and some numbers on the other side, I can solve it to get rid of that logarithm by raising both sides to the power of e. And that's going to eliminate the natural log from one side, and it's going to let me solve the equation. So knowing that these guys are inverses is actually quite useful and quite important, even outside of calculus. But I just wanted to kind of point that out to you so you can kind of know that if you didn't already know that. Now in this section, we're not going to care so much about the fact that they're inverses. What we want to know is what the derivative of this e to the x function is. In other words, derivative of e to the power of x. That's really what this section is about. In the last section, we learned what the derivative of natural log was, which is the inverse of e to the x, right? We learned that the derivative of natural log is 1 over x, and we learned how to do problems here. What do you think the derivative of e to the x is going to be? It turns out that e to the x is a very, very, very special function. When you take its derivative, you get back e to the x. You don't get anything other back than what you started with. And that's the only function that does that with derivatives. Even with sine and cosine, you kind of get close with sine and cosine, because if you take the derivative of sine, you get cosine. You take the derivative of cosine, you get negative sine. So you do kind of flip-flop back and forth with the trigonometric functions, but this is the only function that once you take the derivative one time, you get exactly the same function back that you started with. So you can take the second derivative or the third derivative or the fourth derivative of this function, and you're still going to get that function because it never changed. And I call it, some books might mention it, but I call it the indestructible function. Because normal functions like polynomials, if you take derivatives, eventually they'll disappear. You'll take 3x squared, and you'll take the derivative 2 or 3 times, and then there'll be 0 because there'll be nothing left. But you can take this derivative 10 million times, and the answer you get is still e to the x all the time. So this is a very, very important result, and it's very remarkable that it's the case. And it just kind of goes to show you how special this number is, e. That when you take its derivative, it's equal to itself. Now, it doesn't mean it's mystical. It doesn't mean that it's magical. It just means that if you plot that function e to the x, it just so happens that the shape of that function is very special. So that if you try to look at the slope of the line tangent to that function, which is what its derivative is, then what you're going to get is going to be what the original function was equal to anyway. The shape of that curve is very special, so the values along that curve happen to yield the slope of the curve at all points. That's why it's equal to itself. But in the context of this lesson, what we're going to do, much like in the last one, is take this fact and work a bunch of problems to show you how to take derivatives of functions that involve what we call this natural exponential function. We call it the natural exponential function because it's got a base e there, a very special base. So as our first example, let's start small and go bigger from there. F of x is equal to e to the power of 4x. Now this is not quite the same because here I told you the derivative of e to the x was e to the x. But here we don't have e to the x, we have e to the 4x. So when you think about it, just like before, we have sort of a nested function here. The larger picture function, the big picture, is the fact that we have the exponential, e to the power of something. The details is that what's wrapped up in here isn't quite so simple like just x would be. So it's much like sine of x squared. You have to take the derivative of the outside, then multiply by the derivative of the inside. So to take that derivative, what you're going to have is f prime of x. First you take the derivative of the big picture, which would be e raised to the 4x power because it's indestructible. But then you multiply by the derivative of the inside, which is what's up here, which is just 4. So really, this is a very simple problem to calculate. It's 4e to the 4x, and this is the answer. So a lot of students, when they realize and they learn that e to the x is sort of the indestructible function, they'll leave it here and they'll say, well, the answer is e to the 4x. It's indestructible. Well, you got to use the chain rule. That's true because this is the outside function, but the inside function is 4x. You have to multiply by that guy. Okay? What if you have f of x is equal to e to the power of x to the 5th? So we have e raised to the power of x to the 5th. How do we handle that? Well, again, the larger picture is the exponential, so we start there. The derivative is, since it's indestructible, e to the power of x to the 5th, but we can't stop there. We have to multiply by the derivative of the inside, which is up here. So the derivative of x to the 5th is 5x to the 4th. So the answer to this derivative is 5x to the 4th times e to the x to the power of 5. And that's the answer to this guy. Okay? So it's very, very similar to what we did with the logarithm function, the natural logarithm function. We take the derivative of the outside, then we multiply and take the derivative of the inside, and we keep going in and in and in until we're done. All right? So let's say you have something a little more complicated. Let's say you have f of x is equal to e to the x plus 1 over e to the x minus 1. So here you have to look at the big picture. The big picture is not the fact that I have the exponentials. The big picture is that I have a quotient here. I've got a term on the bottom and a term on the top, and they're divided by one another. So I'm going to use the quotient rule. And then we'll get into the derivative of everything else here in just a minute. First things first. Bottom, e to the x minus 1, times the derivative of the top, e to the x plus 1, derivative, minus the top, e to the x plus 1, times the derivative of the bottom, e to the x minus 1, derivative, over the bottom squared, e to the x minus 1 squared. Bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now it turns out these derivatives are quite simple to calculate, so let's go ahead and do that. E to the x minus 1. The derivative of this guy, when you think about it, the derivative of e to the x is e to the x. Derivative of 1 is 0, so I'm done. Over here, I have e to the x plus 1. Derivative of this guy, e to the x, is just e to the x. Derivative of this is 0, so I'm done there. On the bottom, I'm going to have e to the x minus 1 squared. Okay? So the only thing to do at this point, I mean, this is the answer. You could circle it if you wanted to, but let's try to simplify it a little bit more. Let's multiply these guys in. Now, if I take e to the x times e to the x, I'm going to have e, and I'm going to add the exponents together. So it's going to be e to the x plus x, so it's going to be e to the 2x. So here's e to the 2x by adding these exponents, minus multiplying this term, e to the x. And then over here, I'm going to have e to the x times e to the x, which is again e to the 2x, but I have a minus sign, so it's minus e to the 2x. And then I have another minus sign from this guy multiplying in. This guy's multiplied together, giving me again e to the x. So make sure you understand that. The minus sign comes from here, and we're just multiplying terms in just as before. On the bottom, we're still going to have e to the x minus 1 squared. Okay, so when we have e to the 2x, it's going to cancel out with this negative e to the 2x. And on the top, what we're basically going to have, f prime of x, is equal to, we're adding these guys together, negative 2e to the x. Because it's e to the x plus, or I should say negative e to the x minus e to the x, so it's got two of these guys, e to the x. On the bottom, e to the x minus 1 squared. So the answer is negative 2 e to the x over e to the x minus 1 squared. And that's the final answer. But you see, it's the same process. You're just looking and you're using the quotient rule exactly as we've done for all the functions we've used up until now. It's just that when you get to the derivative part, you have to apply what you've now learned and simplify the results accordingly. Okay? We'll work a few more just to give you a little bit of exposure to different kinds of problems. What if I had tangent of e to the 3z? And I want to find the derivative of y with respect to z. All right? So the outer function I have is tangent, so I have to deal with that first, and then I'm going to multiply by derivatives of the inside as I go. So dy dz is equal to, what's the derivative of tangent? It's secant squared. So we have secant squared of the argument, e to the 3z. Okay? But we can't stop there. We have to multiply by the derivative of the inside. Now on the inside I have e to the 3z. So the bigger picture on the inside is the exponential, so that's indestructible. E to the 3z stands. But I can't stop there. I have to multiply by the derivative of the inside of this inside term, which is the exponential itself. What's the derivative of 3z? It's just 3. So you see, you keep going in, multiplying by derivatives layer by layer, until finally there's nothing else to take a derivative of. So dy dz is equal to 3e to the 3z times the secant squared of e to the 3z. Right? And that is the answer. Okay, our final problem is f of x is equal to x plus 1 e to the minus x. So again, the big picture is two functions multiplied together, this function times this function, so I have to use the product rule. So the first derivative is going to be first term, x plus 1, times the derivative of the second term, e to the minus x, we'll take that derivative later, plus the second term, e to the minus x, times the derivative of the first term, like this. So that's just the thing that we're doing in all these problems, a lot of them anyway. Let's go ahead and take these derivatives. F prime of x is equal to x plus 1. The derivative of this guy, it's an exponential, so it's indestructible. So first you just do e to the minus x, but then you have to multiply by the derivative of the inside, which is this exponent. The derivative of that is going to just be minus 1. Plus e to the minus x. The derivative inside of here is just 1. That comes from what's in front of the x here, and that's it. So again, if you were crunched for time, that would be your final answer. Let's just rewrite it. Equals. You've got a negative here, so let's write this term first. E to the minus x minus, this comes from the negative sign, e to the minus x, x plus 1. And that is the final answer. E to the minus x minus e to the minus x, x plus 1. You could factor out an e to the minus x if you wanted to. That's fine. I'm just going to leave it like that. And basically, I'm just flipping the order of the terms because this guy happened to be negative, so I'm going to move that over to the end. But other than that, it's pretty straightforward. So e to the x is what we call the natural exponential function, or sometimes you might just hear it referred to as the exponential function because it's so important. The base number e is very, very important. The natural log, we talked about in the last section, pops up all the time. The exponential function e to the x pops up all the time. And that's why we take some time to really learn how to take the derivative of natural log in the last section, along with its inverse, which is the exponential function e to the x. We learn how to take the derivative of that. We take the derivative of e to the x. It's a very special function because it's indestructible. You take the derivative over and over again and it just keeps giving you back the same thing. Now obviously, if you have anything other than e to the x up there, if you have anything else up there, you got to keep multiplying by the derivative of the exponent because that's the chain rule. So it's not really a collection of these different rules. It's a core subset of rules that are applied to many, many different functions. And that's sort of the beauty of calculus, seeing the order in it, knowing how to take these complicated derivatives doesn't come from a million different techniques. It just comes from a few techniques that you apply to a million different functions in a million different situations. So I hope you've enjoyed this section. Work these problems. Make sure you understand them. Grab some additional problems from your book. Work those guys. It's very, very simple once you get the hang of it. So I hope that I was able to help you out and do that this time. Work these problems enough times so you feel comfortable in it. Make sure you know how to do them because you definitely will be asked how to take the derivative of these exponential functions on your exams.